dynamics of first order systems. So, our topic is dynamics of first order systems. So, before going to discuss the dynamics of first order system, we will know what is first order system. What is first order system? First order system is one whose output y t is modeled by first order differential equations. Fine. Suppose we have a process this is the input to the process and this is the output to the process. Input is represented by f and output is say by y. Now, first order system is one whose output y is modeled by first order differential equation. Fine. Now, we will consider the linear case, or if nonlinear equation exists, we need to linearize that equation. So, if we consider the linear case, then first order differential equation we can write by this form: a 1 dy dt plus a naught y equal to b f t. Definitely y is also function of time. Now, in this equation a and b both are constant coefficients. A and b are the constants. Fine. F is the forcing function or input. F is the input and y is the output. Now, if we rearrange this equation, then we get a 1 divided by a naught dy dt plus y equal to b divided by a naught function of t. Fine. Now, before this I want to mention one thing, that we will consider two cases. In one case a 1 equal to 0 and in another case a 1 not is equal to 0. So, in case 1 we will consider a 1 not is equal to 0. First we will discuss a 1 not is equal to 0, then in the next case we will consider a 1 equal to 0. Now, after rearranging this first order differential equation, linear equation, we get this. Now, we will represent a 1 by a naught, we will represent a 1 by a naught by the term tau p, and another term, that is b divided by a naught, will be represented by k p. Fine. Then the linearized form of first order differential equation for the case of a 1 not is equal to 0 becomes tau p dy dt plus y equal to k p f t. Fine. Now, this tau p is called time constant of the process. Tau p is called time constant of the process. Definitely we are discussing first order process. So, this is the time constant of first order process, and Kp is called steady state gain. Kp is called steady state gain or static gain or only gain, I mean gain of the process. Fine. Now, what is gain? Gain is basically the change in output per unit change in input. Gain is the change in output per unit change in input. I mean gain equal to change in output divided by change in input. Fine. Since we have considered this as static gain, so this delta output divided by delta input, they should be considered at steady state only. So, we know the modeling equation a 1 by a naught dy dt plus y equals to b by a naught f t. So, what will be the steady state form of this? Steady state form will be, if we consider the first equation, I mean a 1 dy dt plus a naught y equal to b f t. This is the modeling equation. So, what will be the steady state form of this? A naught y s equal to b f s, agree, because this dy dt term does not exist. Now, if we rearrange this y s by f s equal to b by a naught, agree. If we rearrange this equation a naught y s equals to b f s, y s divided by f s becomes b by a naught. So, what is y s by f s? That is again output by input change. That is why we have represented b divided by a naught as steady state gain, fine, and that we have represented by Kp. Now, we will go back to the equation. We got tau p dy dt plus y equal to Kp f t, where y and f both are deviation variables, fine. That is why we have written here this is as delta output and this is as delta input. So, y and f both these variables are deviation variables, deviation variables. That means y naught equal to f naught equal to 0. Can we write this? If y and f both are deviation variables, then we can write y naught f naught both are 0. Now, we will take Laplace transform of this, Laplace transform. Then we get tau p s y bar s plus y bar s equal to Kp f bar s. If we take Laplace transform of this, then we get this form. Now, rearranging the above equation, we get y bar s by f bar s equal to Kp divided by tau p s plus 1. y bar s divided by f bar s becomes k p divided by tau p s plus 1, and this is nothing but the transfer function of the first order system. We will represent this by G s, transfer function of the first order system. Fine. In the next and this is also called as first order lag or exponential transfer lag. This is also called first order lag or exponential transfer lag. We will see later that this transfer function involves phase lag, that is why this is first order lag transfer function. Fine, we will consider that later. So, in the first case we have considered A naught not is equal to 0. In the next case we will consider A naught equal to 0. So, in case 2 we will consider A naught equal to 0. Our original equation is A 1 dy dt plus A naught y equal to b f t. This is the original equation. Now, if we consider A naught equal to 0, then this becomes A 1 dy dt equal to b f t. Fine. That means dy dt equal to b by A 1 f t. This is equal to k p prime f t. Here gain is represented by k p prime and that is b by A 1. Fine. K p prime is here b by A 1. Now, if we take Laplace transform again, then S y bar S equal to k p prime f bar S. Rearranging this form, we get the transfer function G s equal to y bar S divided by f bar S equal to k p prime divided by S. Fine. So, this is the transfer function of a first order system when we consider A naught equals to 0. Now, these type of processes are called purely capacitive or pure integrator. These type of processes are called purely capacitive or pure integrator. For the example first order system with A naught equal to 0, we got the transfer function this, and this type of processes are called pure integrator. We will discuss with physical example what type of processes are called pure integrator process. Fine. Now, these are about the transfer functions in general form. In the next we will discuss with some example. We will first consider one example, that is a liquid tank system. We will consider an example, that is a liquid tank system. This is a liquid tank. Height of this liquid is h. Cross sectional area of the tank is suppose A. Input is entering the tank with a flow rate of Fi and output is F, and here we are considering resistance, that is R. Fine. Now, this effluent flow rate F is related to the hydrostatic pressure of the liquid height h through resistance R. Here R is the resistance to flow, resistance to flow. Fine. This F is linearly related to the hydrostatic pressure, to the hydrostatic pressure of the liquid level H through resistance R. Fine. Effluent stream, effluent outlet we can represent by this form: F equal to driving force for flow divided by resistance to flow. Resistance to flow. Fine. It is quite common in heat transfer also, like Q equals to delta T divided by R. We have studied in our heat transfer course, rate of heat transfer equals to driving force, that is temperature difference, divided by the resistance. Similarly, we are writing also the same similar equation, similar relationship, that is F equal to driving force is here H and resistance is R. Fine. So, in the modeling equation we will consider F equal to H divided by R. What is the modeling equation of this liquid level system? We have derived the modeling equation for this liquid level system earlier, that is A dH dt equal to Fi minus F. Fine. Fi and F both are volumetric flow rate. Fi and F both are volumetric flow rates. Now, if we rearrange this equation, we get A dH dt plus F equal to Fi. If we rearrange the modeling equation, we get this. Now, we will substitute F equals to H by R. Then we get A dH dt plus H divided by R equal to Fi. Multiplying both sides by R, we get A R dH dt plus H equal to R Fi. fine. Multiplying both sides by r, we get this equation. Now, we need to represent this equation in terms of deviation variable. So, for that we need to consider the equation at steady state. What will be the form of this model at steady state? It will be H s equal to R F I s. At steady state condition, the above modeling equation, I mean this modeling equation becomes H s equal to R F I s. We are using suffix s to represent the steady state. Now, subtracting this steady state model from this modeling equation, we get the equation in terms of deviation variable, that is A r d h prime d t plus h prime equal to r f I prime. Fine. Subtracting steady state model from this original model, we get this form in terms of deviation variables, where h prime equal to h minus h s and f I prime is f I minus f I s. These two deviation variables are involved. Now, we can replace A r by the time constant. Time constant we have represented by tau p, and here tau p equal to A r. Fine. So, what is the unit of this tau p? Can you find the unit of this tau p? Unit of this tau p is time. Similarly, we will consider K p. K p is here r. So, that will be the unit of r basically. What is the unit of r? R equals to h by r, that means time per meter square or time per area, we can say. Now, we will just replace this A r term here by tau p and r by this K p term. Then we get tau p d h prime d t plus h prime equal to K p f I prime. Fine. Again we will take Laplace transform of this. Then we get tau p s h bar prime s plus h bar prime s equal to K p f I bar prime s. Now, if we rearrange, then finally we get h bar prime s divided by f I bar prime s equal to K p divided by tau p s plus 1. So, here K p is basically the resistance, tau p is A r s plus 1. This is the transfer function of this system, liquid level system. Now, here you see one thing, tau p we have considered, that is time constant equal to A multiplied by r. Now, we can write this as storage capacitance multiplied by resistance to flow, resistance to flow. Fine. Now, the capacity to store mass is measured by the value of A. The capacity to store mass is measured by the value of area A, and this is obviously resistance R. Similarly, if we consider one example which includes only the energy balance equation, in that case this storage capacitance is basically the capacity to store energy. Fine. If we consider an example which is modeled by only energy balance equation, in that case also we can write this time constant tau p equal to storage capacitance multiplied by resistance to heat. Then in that case this is the capacity to store energy, not mass. Fine. In the next we will take another example, that is the pure capacity system. We have considered another example, that is the example of pure capacitive system. I mean, how we can get the A naught y term equal to 0 physically? We will continue the liquid tank system which we considered earlier. So, this is a liquid tank system, height is h, area is A. Inlet flow rate is F(i). In the outlet section, one pump is installed, which is delivering outlet with a flow rate of F. In the outlet section, one pump is installed, which delivers the outlet or effluent stream with a flow rate of F, and this is a constant displacement pump. This is a constant displacement pump. It means the flow rate is constant, I mean F is constant. Fine. So, we have already considered the model of this system in the previous example, that is F dH dt equal to F(i) minus F. This is the modeling equation for the liquid tank system, and this is the linear equation. So, there is no need of linearization. Now, this is the modeling equation. Fine. What will be the equation at steady state? At steady state we get dHs dt, which is nothing but 0, equal to F(i)s minus F. I told that for the case of constant displacement pump, F is a constant or F remains constant. Fine. Now, subtracting this steady state model from the actual process model, we get the equation in terms of deviation variables, that is this. Subtracting the steady state model from the actual process model, we get this modeling equation in terms of deviation variables. Fine. Now, what will be the transfer function of this? if we take Laplace transform again A S h bar prime s equal to this. So, h bar prime s divided by f I bar prime s equal to 1 divided by A s. That means 1 divided by A whole divided by S. If we write in this form K p prime by S, then here K p prime is 1 by A. This is one example of pure capacitive process. Fine. Next we will discuss the dynamic behavior of first order system. Previously, it was told that the transfer function is used to observe the transient behavior of a process. Fine. Now, that we will discuss by the use of transfer function how we can know the transient behavior of a process, that we will discuss in the next. So, first we will consider the dynamics of a first order system considering input as ramp input. So, next topic is dynamic behavior, and we will consider first order process, and we will change the input as ramp function. I mean the input is ramp input. This we will discuss in the next. So, we have already derived the transfer function of a first order system in general form, that is G s equal to y bar s divided by input, that is K p divided by tau p s plus 1. This is the transfer function of a first order system. This is the transfer function of a first order system. Fine. Now, to observe the transient behavior, we need to introduce some change in the input. To observe the transient behavior of a process, we need to introduce some change in input variable. Now, here we will consider ramp input. So, f is the forcing function, f is the input to this process. We will consider here f t equal to a t, and this is the ramp function. Now, in Laplace domain, in S domain, we can write this as a by a square. Fine. This is the form of ramp function in S domain. Now, our transfer function is y s divided by f bar s equal to K p divided by tau p s plus 1. If we consider f s equals to a by a square, then the output in S domain becomes K p a divided by a square tau p s plus 1. Got it? Considering f s equal to a divided by a square. Fine. Now, we will just write this form in this way: C 1 divided by tau p s plus 1 plus C 2 divided by s plus C 3 divided by a square. And finally, we will get y bar s equal to k p a tau p square divided by tau p s plus 1, and next term k p a tau p divided by s. Third term involving C 3 becomes k p a divided by a square. Fine. After introducing ramp input to the process, we get this is the output in terms of in Laplace domain. Fine. Now, if we consider the inverse of Laplace transform, we get y t equal to k p a tau p exponential of minus t divided by tau p plus t divided by tau p minus 1. Taking inverse of Laplace transform, we get this form in time domain. Fine. If we rearrange this equation, we get k p a tau p exponential of minus t divided by tau p plus k p a t minus tau p. Rearranging this equation, we get this form. Fine. Now, we will consider one case, that is t tends to infinity. If we consider t tends to infinity, then y t becomes k p a t minus tau p. Fine. That means, we can say that the ramp input yields a ramp output with slope k p a. This is the slope. We can say that the ramp input yields a ramp output with the slope of k p a. And if we represent this graphically, then we get this plot. This is time t, this is y t. This is y t equal to a k p t minus tau p. This is the tau. I mean tau p, this is 0. fine. So, we can say that the ramp input, as I told, yields a ramp output with the slope of Kp a, fine. Next, we will consider the purely capacitive process, dynamic behavior of a pure capacitive process. This is the dynamic behavior of the first order system considering ramp input. Next, we will discuss dynamic behavior of a pure capacitive process considering step input, fine. So, dynamic behavior pure capacitive process dynamic behavior of pure capacitive process considering step input. Fine. Now, you can recall the first order system model A1 dy dt plus A naught y equals to B f t, and considering A naught equal to 0, we got y bar s divided by f bar s, that is equal to K p prime by s, and this is the transfer function of a pure capacitive process that we have derived earlier. This is the transfer function of a pure capacitive process, fine. Now, we will introduce a step change in input variable. So, f t we will consider equal to 1. I mean, this is a unit step change. To observe the transient behavior of a process, we need to introduce some change in the input variable. So, for that we are considering a unit step change. So, in Laplace domain we can write this as 1 by s, fine. Then what will be y bar s? Y bar s becomes K p prime divided by s square, because f bar s equals to 1 by s, fine. Now, we will take the inverse of Laplace transform. Inverting, we get the output in time domain equal to K p prime t. This is a linear equation, fine, with slope K p prime. Now, we will represent it graphically. If we consider t tends to infinity, what happens? Y t tends to infinity, fine. So, this is y t and this is time t. This is the output and slope is K p prime. This type of processes are called non self regulating process. this type of processes are called non-self regulating systems. Question is why? We will consider one system, that is liquid tank system. To explain this concept, we will consider one liquid tank system. In fact, we have considered this earlier also. One constant displacement pump is installed here, H A. Fine. Now, we are introducing a unit step change in F I. We are introducing a unit step change in F I. Then what happens? The height increases, because this pump is delivering constant output. So, height gradually increases with time. Agree? So, if we consider here positive change, I mean if we increase F I, then the liquid in the tank, I mean the height of liquid in the tank increases, and this tank becomes, I mean this tank is flooded. Agree? So, flooding takes place. Similarly, if we decrease F I, then height decreases, because pump is delivering constant quantity and the tank becomes empty. Fine. That is why we called this process as non-self regulating process. Fine. If there is no pump, you see the fact, if there is no pump, with the increase of F I, the height increases instantly, then hydrostatic pressure increases, which in turn increases the outflow rate and equilibrium is established, that is basically the new steady state. In that case, we use the self regulation term. If there is no pump, this process is called self regulating process. Fine. Anyway, next we will consider another dynamic study, that is the dynamics of first order system considering step change. Previously, we have considering ramp change. So, now we will discuss dynamic behavior of first order systems considering step change. So, the transfer function of a first order system is K p divided by tau p s plus 1. This is the transfer function of a first order system. Now, we will consider step change with suppose magnitude A. This is step input. Fine. That means f bar s equal to A by S. Agree? Then y bar s becomes K p A divided by S into tau p s plus 1. Now, we can write this as k p a multiplied by 1 divided by s minus tau p divided by tau p s plus 1. Fine. Taking inverse of Laplace transform, we get the output y in time domain as k p a 1 minus exponential of minus t divided by tau p. Fine. This is the process output of a first order system subjected to step input in time domain. Now, here y is the deviation variable. Deviation variable. Fine. Now, in the next class we will discuss the graphical representation of this system, I mean first order system subjected to step input. Thank you.